Hi, I would like to show you how I created a capacitance mirror using really simple parts you can get from an electronic store or from off-the-shelf parts. Uh, I decided to create a capacitance mirror because I have wanted to know precisely the values of some of my capacitances so I can estimate more precisely what I'm supposed to measure, and so in the simulations have a even more approximate simulation of the circuit. This came from my background as a physicist, as I like to have a good approximation of my model. So the closest I have, the better will be my predictions in the future. So also, I don't have the money to buy a real capacitance meter, which leads you to build one of yourself, honestly. So, okay, let's begin with this. The circuit you are watching right now is really, most of it's not it. The circuit I'm trying to show you is this little bit right here. It's simple, really simple to make, and it doesn't require an ADC, nor it requires more than digital circuitry. So I will show you how my circuit works. Okay, so my microprocessor, which in this case is a Teensy, I'm using a Teensy because it has a higher clock speed than an Arduino, but theoretically it is possible to use an Arduino as well. I'm using a relay to switch between two resistors, and here it's the output where I should connect my capacitance. So I will now go into further detail of the circuit. So the Teensy outputs a square wave as shown in the screen, around 10 milliseconds wide, or with a period of 4 milliseconds. It goes through one of the two resistances, then it goes through my test capacitance, which in this case I'm going to use a 10 nanofarad capacitance. So now over here you can see that it is showing a number. That is the number currently measured by the capacitance mirror. Oops. And what I'm measuring is that, really simply, I'm measuring the delay caused by the capacitor over here. Let me show you what I meant. Let me price this bit right here. Oof. Almost there. There we go. Okay, as you can see on screen, I'm pretty much delaying the square wave just slightly, and the Teensy is pretty much measuring that delay in as close as possible. If I change this capacitor, let me show you. This is a 100 nanofarad capacitance. As you can see, the delay is changing again. The delay is caused because pretty much this is a low pass filter, so all the high frequencies of the square wave are being cut off, and we have this resulting square wave. Or in other words, the capacitor is being charged and discharged, and I'm measuring the time it takes it to being fully charged and time it takes it to being fully discharged. In my circuit, I measure the fully discharge time, because I found out that the the input impedance of the Teensy, it's lower when it's discharging something than it's to, or more precisely put, when it's sinking than when it's sourcing. My circuit works by with a microcontroller, which in this case is a Teensy. Its output, it's a square wave as shown in the image, and then it goes through one of the two resistors right down here, and the relay is pretty much working as a multiplexer, choosing between the two resistors, which the microcontroller seems more fit, and then it goes through the capacitor. The transistor and the diode over here, it's pretty much the driving hardware for the relay, so that shouldn't be, I will not go behind that. Right over here I have a display which shows the capacitance. I wanted to use a segment display because I want this to be a standalone item, which pretty much I can use a power supply and just use it as it is, and no computer has to be connected to it. And the display shows three digits, well, three numbers. As you can see, I'm showing 9, 15, 10. The first two numbers are the four most significant digits of the capacitance. That means I'm measuring 9, 15, and the last digit, which is in this case 10, is the exponential of the or the power of the number. That means I'm measuring 915 times 10 to the power of 10. This means that this capacitor is 90.5 nanofarads. Really good. Let me put this 10 nanofarad one now. Just give it a moment. Stop working. Oh, there you go. It stopped working because the relay is kind of clumsy. Okay, with this capacitance, I'm showing 907 times 10 to the power 11. That means I'm measuring 9.06 nanofarads, which is within the spec of this capacitance. This is another 10 nanofarad capacitance, but from a different company. I'm measuring 997 times 10 to the power 11, which is 9.96 nanofarads. This is a better capacitor if I wanted more precise measurements. This is another 100 nanofarad capacitance. (964) times 10 to the power 10, that means it's 97 nanofarads, which is also within the scope of this. Now, the limits of this circuitry all really depends on the minimum time measurements I'm able to make and the resistors I'm able to choose. For example, right now I can delay the circuit even more and use even higher resistor values, but the problem is that the higher this value is, the more noise it is included in the measurement, just because of thermal noise coming from the resistor. Also, the higher the resistor, the higher the pulse has to be. Right now I'm using a 4 milliseconds pulse, which is quite slow. So if I wanted to make even more precise measurements, I have to make this pulse even larger, so it will make the measurements even slower. Right now, as I have measured, this is one of the biggest capacitors I'm able to measure, and I can calculate that based on my resistors and my resistors. This is 949 nanofarads. No, 548 nanofarads. I'm sorry. This is pretty much the limit of my circuit because, as you can see on screen right now, the square root is so it's so different that even higher capacitance will not fully charge the capacitance. Right now, I will not trust this measurement because this circuit is expecting that the capacitance is being fully charged. If it's not fully charged, then this measurement isn't working. It will not work. I will not trust this measurement right now. And if I wanted to fix this, I have to make the pulse even bigger in time, but that will make the measurements take longer. And they will take longer because the measurements are not being made by one measurement. They are being made by taking the mean or the average of all of 64 independent measurements. So if I wanted to make it less precise, I could probably reduce it to 16 or 8, and it will be faster. But I want to the deal with the goal with this circuit is I want it to be as precise as possible. I want that the resolution of my digits right here is the error of my measurement, pretty much. This is another one. 658 times 10 to the 11th, which I think is 6.5 nanofarads, which makes sense. It has a marking of 683, which is the same value. It's another one. I think this one is the lower limit of my capacitance mirror, and as you can see, it is not showing anything. And if you see the square wave, it hasn't changed at all. If I remove it, you can see pretty much nothing. It has changed. That's because of my resistors I have choose. If I wanted to measure even lower capacitances, I will have to increase these resistors, and as I have explained before, that's a problem. This is also not a small capacitance, 96812, so 867 picofarads. Have been able to calculate what is the minimum capacitance of my measurement, which is around 250 picofarad. That's because of the time I'm measuring pulses, delay pulses as low as 25 microseconds, and I'm not going lower than that because of the inherent noise coming from the averaging and the noise coming from the measurements and all of that. Probably I could go as low as 20, which will decrease the minimum capacitance, but for now I have not experimented with that. And the higher, can be half of the pulse width as my the pulse lasts 2 milliseconds, so the maximum time I can measure is 1 millisecond. No, yeah, it's 1 millisecond. I'm sorry, it's 1 millisecond. So when inputting that to a formula I have calculated, I found that I can measure around 500 nanofarads, uh, and that's within this the and when I try to measure nanofarads bigger than that, I noticed that the measurements are not precise and I will not use them. For example, with this capacitor as I showed, and for now, the most of the complexity regarding this circuitry is coming from the code inside the microprocessor. I probably could go into details of that if anyone is interested. But it is pretty much it's really that simple. It's really simple. For now, it is only outputting the square wave, measuring, and if it measures values higher than some value or lower than some value, it switches between the two resistors. It also averages the values that I'm measuring. It also controls the display, and it also, watch, I'm going to call detects that a measurement is being made. If nothing is being made, it will try to change between the two resistors and turn off the display. And for what it's worth, that's all the software does. However, if someone likes me to go a bit further, I could. On a future video, I will try to explain the circuitry all over here. This is for another type of measurements I'm trying to make, but instead of capacitances, I'm measuring inductances. But that's another video for another day. And well, thanks for watching, and that's everything for now. Thank you.